Hi students, welcome back. Today I'm going to show you an application of simultaneous equations in physics, in particular in electricity, that is in circuit problems. So here is a problem, a multi-loop circuit problem in which we want to determine the electric current in the various branches of the of the circuit. So if you don't understand if you don't understand this at this point, please don't worry, you will learn it in college physics. For those of you who have already seen it, here you will see the use of system of equations. We start with setting up currents in these loops. This one we say is I1. The same I1 flows in here. Then it splits up into I2, and this one here is I1 minus I2, and that is the same current that also flows over here. We draw the directions in which we will apply the Kirchhoff's laws. We will do clockwise in both loops, so I have marked that. And now we will start writing the equations for the Kirchhoff's loop law. The way we do that is we go around the loop and we calculate the rise and drop in voltages. I will start here behind the 9-volt battery, and I will start writing the equation for this. A rise in voltage 9 volts. Then as it goes, a current of I1 goes over the resistance 1 ohms. There is a drop in voltage which is equal to the current times the resistance 9 minus I1. And then as it goes over this second resistor, another I1, and as this goes over the 4 ohms resistor. Now notice that in this branch of the loop, the current is actually I2 and not I1. So whatever that current is, we utilize that. Um, we multiply the resistance and the current, and so that is 4I2, and so another drop in voltage minus 4I2. Then we are going opposite to the battery, so that causes a drop in voltage minus 6 volts, and then we come back to our starting point. So all of it together is 0. This is our first equation, and in this I1 and I2 are the two variables. Okay, let's simplify this a little bit, collecting this minus 2I1 minus 4I2, and here we've got 9 minus 6 on the left hand side, so that is plus 3 is equal to 0. I will divide by 2 all over and move these to opposite side of 3 so that they become positive. So when I divide by 2, this will be I1 plus 2I2, and then 3 divided by 2. So this is equation number 1 in our system of equations, and I'm going to name it as 1. Now let's write the equation for the second loop, which is the second loop that goes over here. Again, I will start behind the 6-volt battery, and as we go over here, we will have a rise of 6 volts. And then here's the interesting part: because we are going opposite to the current, instead of a drop there will be a rise, so we will say plus 4I2 as we go over this resistor. Then nothing happens while going over here, and then as we go over on this side, the value of this R is not given. Let's say this is equal to 10 ohms. As we go over this, there will be a drop in the voltage, so minus 10 I1 minus I2. After going here, as we go over this battery, there's a minus 3 volts, and then we get back to the starting point. So our equation is complete. Simplifying this, 4I2 minus negative 10I2, so that is 14 I2 minus 10 I1 and I've moved this 6 minus 3 is 3 on the left hand side. I've moved it to the right hand side, and that becomes minus 3. I will do a further simplification. I will divide on the whole equation by 10, so that this becomes 1.4 I2 minus I1 is equal to negative zero point 0.3. There is a purpose of why I decided to do that. I'm following the elimination method, and I can already see that in equation number 1, I1 has a coefficient of 1. So I tried to make the coefficient of I1 the same here by this division, and so our life will be easier. So this is equation number 2. Now let's put these equations one under the other and see what happens. So I1 plus 2I2 is equal to 1.5. So that is equation number 1. Now we can simply add these two, because by adding these two the I1 will be eliminated. So 2 plus 1.4, so this is eliminated, and as far as I2 is concerned, 2 plus 1.4 is 3.4. I2 is equal to 1.5 minus zero point 0.3, so 1.2. I2 is equal to 1.2 divided by 3.4, 0.35. So we got the answer for the value of I2. And then the question is, how much is I1? So that we can obtain by using any one of these equations. Use this equation number 1 to calculate I1. So I1 in terms of I2 is 1.5 minus 2I2. So 1.5 minus 2 times 0.35, which is the value of I2. So 1.5 minus, and this becomes 0.7. So the answer is 0.8. And then what is I1 minus I2? I1 minus I2 is 0.8 minus 0.35, which is 0.45 amperes. All these currents are measured in amperes. So those are our answers. All right, so this branch had I1, and I1 is equal to 0.8 amperes, and that current of 0.8 amperes runs in this whole branch. All of it that I have marked with red has 0.8 amperes. And then I2 is 0.35 amperes. So here this is 0.35 amperes, and that is the current flowing in this branch over here. And then I1 minus I2 is the current that is going in this branch here. And that is equal to 0.45 amperes. And all of these numbers came out to be positive. That means the current directions that we had assumed initially were correct. If those came out to be negative, then we would say that the current is flowing in the opposite direction of what we chose. So this is an example of an actual application in physics of system of equations. Thank you.